This is the sound of Sputnik, the very first artificial satellite launched by the Soviet Union in 1957. In 2018, SpaceX launched Elon Musk's Tesla Roadster into an orbit around the Sun. Sputnik fell back to Earth just a few months after its launch, and Elon's Tesla is now just an uncontrollable piece of space debris.
What a piece of junk!
There are around 1,700 operational satellites currently orbiting Earth and beyond that we still communicate with. But how exactly do we communicate with objects in space? In this video, we're going to look at the different ways we communicate with objects, all the way from low Earth orbiting satellites to deep space probes at the edge of our solar system. We're also going to talk about the equipment that's used and how the capability of that equipment has to grow in order to deal with the increasing amount of data we are collecting from our solar system. Say you wanted to send a command to a satellite placed at a geostationary orbit 36,000 kilometers above the Earth. Firstly, the command gets converted into a radio wave, which is a type of electromagnetic radiation that travels at 300,000 kilometers per second, the speed of light. Once the command is converted into a signal, a ground station antenna will then transmit that signal towards the satellite, which will use its very sensitive antenna to receive the signal. Then, the onboard systems will convert that signal into code, which the onboard computers can understand. Most satellites will have an uplink and a downlink to allow the satellite to send data back to Earth. In 1962, NASA realized that it would need a brand new communication system for the Apollo missions. Not only would the Apollo missions be going much further than the previous missions, they would also be communicating with 3 astronauts working in 2 different spacecraft, as well as sending telemetry and live television images back to Earth. They developed a system called Unified S-band, which could send telemetry, command, voice and television data using different frequencies but combined into a single antenna. This system would communicate with the Apollo spacecraft via fixed ground stations placed around the Earth. This would allow mission control to have continuous communication with the astronauts during the mission, apart from when the spacecraft curved around the far side of the Moon, where the signal would be lost until they reappeared on the other side 40 minutes later. During this time, the astronauts had to fire up the engines in a critical maneuver to make sure they reappeared on the other side of the Moon. If the crew had a successful burn, it would set them on the expected trajectory, meaning mission control knew exactly when they would regain communication with the Apollo 8 crew.
Apollo 8, Houston, over. Apollo 8, Houston, over. Houston, Apollo 8. Very complete.
We've got it. Apollo 8 now in lunar orbit. There's a cheer in this room. This is Apollo Control, Houston. Switching now to the voice of Jim Lovell.
Of course, this loss of signal can also happen to satellites orbiting Earth, when the transmitter has no clear path to the satellite. To get around this, NASA set up the Space Network, which uses satellites in geostationary orbits to relay data from other satellites to fixed ground stations. This provides continuous global coverage for all Earth orbits. The Space Network may cover satellites in Earth's orbit, but what about satellites that are much farther away? The farthest distance a satellite can orbit the Earth before the gravitational force of the Sun equals that of the Earth is around 1.5 million kilometers. But what about satellites that are billions of kilometers away? The farthest man-made object from Earth is the Voyager 1 space probe. It was launched in 1977 to study the outer solar system. It is currently 20 billion kilometers away from Earth and traveling at 62,000 kilometers per hour. The transmitters used by the Space Network aren't powerful enough to reach and receive data from deep space satellites. For satellites this far away, we need something called the Deep Space Network in order to communicate. The Deep Space Network consists of antenna complexes at 3 locations around the world in America, Spain, and Australia. These facilities are equally spaced, 120 degrees apart on Earth. Each complex has a 70-meter antenna, as well as 2 smaller, high-efficiency antennas. Satellites close to Earth typically use low-gain antennas, which spread their signals in every direction, making it relatively easy to pick them up here on Earth. Satellites in deep space use high-gain antennas, which focus their radio waves to achieve a much stronger signal strength once it reaches Earth. The demands placed on deep space communication systems are continuously increasing. As of March 2016, the Mars Reconnaissance Orbiter had returned more than 300 terabits of data. And as we continue to launch more and more satellites into deep space, NASA estimates that our space communications capability will need to grow by a factor of 10 in the next decade. So as we continue to look farther into space, it's good to know that the brave little spacecrafts that we send out to the edges of our solar system are able to talk back to us and tell us what it's like out there.